I'm starting the stream. I'm making sure that I actually have the stream started. So let's go over to live. It says I'm live. And I can see my own stream. I won't be able to check the chat just because everything's all on one window. I don't have like two computers going on. Now we have my infinite scrolling over there. So I'll close this out. Oh, we'll minimize it for now. And we're coming back to what I wanted to do was kind of wrap up this. We were working on our 4-bar linkage, and really, to me, the most important thing we did was go through this step of like, how do I describe constraints with vectors? And really, that's what we were doing here, is taking an understanding. I'm just making sure that I'm muted so I'm not listening to myself. There we go. How do I take my like kind of intuitive understanding of like, yes, these links at positions O, A, B, and C, they're all connected together, but how do I turn that into a math equation where I can start doing some analytical work, like actually predicting based on where angle 1 is, how do angles 2 and 3 respond. So to me, that's the most important part. From there, we start getting into like trigonometry definitions, like, okay, here is the position based on angle. And then we start dealing with, now we take derivatives of that. We remember the product rule. We came up with kind of a general definition for like, hey, look, we have these functions that are functions of time. If I take a derivative, I need both partial with that x and derivative of the x. And end result is that we come up with, if we have a vector equation describing constraints, it'll give us 2 or 3 equations that describe those constraints. And because we took derivatives, the constraints are telling us what are the constraints on speed. So based on how fast theta dot is moving, what are theta 2 and theta 3 dot? There are certain cases where theta 2 dot is always 0, like if maybe it's never spinning. If L1 and L2 are equal, it might move around in a circle. So then you have no rotation. So then L1 theta 1 dot has to be equal to that L3 theta 3 dot. But anyway, in this case, we have something a little different. And I wanted to finish up kind of talking about this. So if I'm looking at this, let's get rid of these and go back to this idea. So I know this position A is given as L1 cosine theta 1 and L1 sine theta 1. And that's really, it's describing this RA term, which is given right here. So I already know exactly what the values are for L1 cosine theta 1 and L1 sine theta 1. And that is a negative 0.2 along the I and a 0.146. Yeah, we'll do 6. It's fine. Along the J. This cosine theta is L1 times, we'll call it like XA over L1 along the I plus L1 times YA over L1 along the J. So I have those cosines and sines already kind of defined. Because if I think about this like unit circle, this is theta 1, this is XA, this is YA, here's my point A, and this is L1. So opposite over adjacent is L1 over YA. Opposite over hypotenuse is L1 over, is YA over L1. Adjacent over hypotenuse, so SOHCAHTOA is, so I already have kind of the values here. So if I divide this by this negative 0.2 divided by L1, that is my cosine theta. So cosine theta 1 equals negative 0.2 over L1. Sine theta 1 is 0.146 over L1. And I can do same thing for this theta 2 and theta 3. So I'll start with theta 3 since that one, well, might as well go in order, right? 1, 2, 3. So now I know something about this RB and I know RC, but I don't have really this, how do I want to draw it? I'll draw it on there and then delete it. That yellow line, that's RB. That has nothing to do with it. It's not that it has nothing to do, but it's not theta 2. It's not a measure of theta 2. So that's not what I want to do. I'm going to get rid of that. Really what I need is RB minus RA, because I'm trying to find this. So RB slash A equals RB minus RA. So cosine theta 1 is going to be this x direction of that B location plus this x direction of that A location, all over L2. So L2 is my hypotenuse, and I'm going to say that it's 0.494 minus a negative 0.2, so plus 0.2. That sine theta, sorry, that should be a 2, is going to be this RB minus this RA part, because I'm not traveling up this whole way. So I don't want this, I only want this part. So that's going to be my 0.863 minus 0.494 all over L2. Cosine theta 3, this is a similar problem, but we happen to have along the y direction, CB, there's no difference in height. So the sine component is just going to be the actual RC. Well, since we just have that J, the 0J. But in the X component, really I just want this distance. So I have to take this value minus this value. Well, 1 minus, so let's just do it. We'll say that it's equal to that 0.863 minus 1 all over L3. And that sine theta 3 is, in this case, it's that 0.863. Oh, why did I do that? Oh my God, I'm mixing things up. Sorry about that. Let me rewind. All right, redo. I want to take the X component and this X component. Oh my goodness. So 0.494 minus 1 over L3. There we go. Oh my God. Long days, huh? And then now I'm talking about that 0.863 minus 0 over L3. Now I've got those two terms. And And whether it's a positive or negative value for the cosine and sine, this cosine theta 3 should be negative because going from C to B, I have to travel in the negative x direction. So intuitively, I know at this point that that's the way it should be set up, that I should be starting with the B and then subtracting that 1. Yeah, and then I do the same thing here, B minus C, just like that. So position B minus position C. Cool. Now I have all of the terms that I need to solve these two equations and two unknowns. So I've got, I'll write out everything. L1 theta 1 dot sine theta 1 plus L2 theta 2 dot sine theta 2 equals L3 theta 3 dot sine theta 3. And I can start replacing this stuff. So sine theta 1 was 0.146 over L1. Really, the L1s cancel out. And then sine theta 2 was 0.863 minus, I'm going to say 0.5 over L2. And these L2s cancel out. And then sine theta 3, 0.863 over L3. Really, those L3s cancel out. So that's my equation 1. Equation 2 is L1 theta 1 dot times cosine theta 1 plus L2 theta 2 dot cosine theta 2 is L3 theta 3 dot cosine theta 3. Now I can plug in those sines and cosines, so delete that. And I get a negative 0.2 over L1, and I'll cancel those out. Cosine theta 2 is 0.694 over L2, and I'm going to cancel those out. And then cosine theta 3 is a negative I'm going to call it negative 0.5 just because I don't feel like keeping track of the other ones. Cool. So now I have two equations with two unknowns. So I'll plug in the last value because I know that this link is rotating at 10 radians per second. So let's get rid of this, get rid of that, call this 10 and 10. So the only things in this equation that I don't know, and there's no other way for me to, I can't use trig to solve this. Like I have to use these constraint equations. I have to use those constraint equations to get to theta 2 dot and theta 3 dot. From here, you've probably seen like different ways of solving two equations and two unknowns. A lot of people will go through and say like, okay, let me solve for theta 2 in terms of theta 3 dots and plug that into the next equation. Then you get one of those values. I'll show you the way that I like to do it at least. So I like to take everything that I don't know, plug it into the left-hand side. So I am going to say a theta 2 dot times 0.694 minus theta 3 dot times 0.863 equals everything that I do know, 1.46, because I took that 10, multiplied it through, and then a theta 2 dot times, oh, I messed that up. This should be a 0.363. And definitely check my math, right? Because I'm doing it here on the fly. And now This one is times a negative 0.2. Then I'm going to subtract or add this theta 3 dot times 0.5. And all that's equal to 10 times negative 0.2, so negative 2. And the reason I go through that effort is that now I can take the stuff that I know and put it into a matrix. And some people are like, ah, matrix, you're trying to trick us. This isn't linear algebra, but linear algebra is so helpful. So stick with me. Negative 0.863, a negative 0.2, and a 0.5 times the stuff that I don't know, a theta 2 dot, a theta 3 dot, and all that's equal to 1.46 and 2. So I have all this stuff that I know. This is known. This is known. And then just this one little vector of things that I don't know. Like, what is this? Now I can plug this into a computer, I can plug it into a calculator, but there's lots of solutions to this linear algebra problem, because what I did was say A times this known A times this unknown X equals a known B. And you can solve this by, you could invert the matrix, or really better is like Gaussian elimination to solve for theta 3 dot and then solve for theta 2 dot. Or I can plug this in. Okay, I can say, all right, here's my matrix A, here's my vector B, tell me what X is, and that's what I'll try here. So we'll take this, push it over to the side, and I'm trying to zoom out. Well, this is okay. Take that, go over to NanoHub. We're trying to get into N dynamics. And it's popping up. Should have loaded this up before, but it's coming. It's coming along. Okay, cool. So I'll come down into the homework too. Just why not? And let's just and all we really need is NumPy at this point. So A is a NumPy array. It's going to have 2 rows, 2 columns, so 0.363, a negative 0.863, and then it'll have a negative 0.2 and a 0.5. My B is also an array, but it only has one either row, it's only one dimensional, 1.46 and 2. np.linalg.solve of A, I don't know why it's giving me AA. Ooh, that can't be right. What did I do wrong? Because this is very fast to be spinning at 280 radians per second. So I did something wrong up here, at least when I entered in this stuff. So let's come back up. Negative 0.2. Is that one? Oh yeah, negative 0.2. So there's my cosine. cosine theta 1, cosine theta 2, 0.694, cosine theta 3, we just called it like a negative 0.5, just rounded, and that should be fine. And now the sine theta is 0.146 is my sine theta 1. 0.863 minus 0.4, so minus 0.5, 0.363 should be okay. And then 0.863. This should be okay. I'm missing something though, because these numbers can't be right. So then what did I do wrong here? Oh, this should be a negative 2, right? Well, one of these should be, all right, maybe that was the problem. I missed a negative sign. Still, 100 radians per second. That's way too fast, because we're only moving at 10 radians per second. It's supposed to be easier when we use a computer, but I missed something along the way. Maybe I did my math. I'm sure I dropped a plus or a minus sign. So let's see. Sine theta 1 should be 0.1459 over L. Oh wait, L1. No. What did I do wrong here? Let's see. So RA, let's go through this RA. This is negative 0.2. So cosine is negative 0.2 over L1. Sine is 0.146 over L1. And that's what I have here. Times 10 radians per second. Now theta 2 should be over L2, but it's 0.494 plus negative 0.2, so 0.694. And then sine theta 2 should be this 0.863 minus that 0.5 of A all over L2, because that's the hypotenuse. Cosine theta 3, it's going to be over, so getting back to B should be a 1 or 0.494 minus 1. That's how far back I need to go. And then this is 0.863. So when I bring, so the cosine components are negative and negative. So when I go here, that should be a negative. And then the sine components, oh wait, that one's our sine components. This is our cosine components. A negative and a positive, but our sine components should all be positive, so it should be positive, positive. This one should be negative, that one should be positive. Because I'm taking this positive number, moving over to the right. So multiply by -1. Move that one, multiply by -1, which would make it positive. Does that fix it? Let's see. So this is positive cosine, or positive sine, so it should be positive negative. This one is positive cosine negative. So two of these should be the same sign. I think these should be the same sign. Those should be opposite. And then this one goes there. Oh, get rid of that insert. That looks better. So I'm moving at 10 radians per second. Theta 2, so theta 1 is increasing at 10 radians per second. Therefore, theta 2 is decreasing at 60% of that, 69%, so 6 radians per second. Meanwhile, theta 3 is also decreasing. Why is it decreasing? Something's weird with my signs. Really doing. So theta 3, that should be a negative, and this should be a positive. So a negative 0.863 times that theta 3 dot. This one's positive. Meanwhile, my sine components should be a positive theta 2 sine, and so these should both be positive because it's a positive and then a negative negative. 2.8, 2.9. Definitely double check the math, but we're getting, this seems a lot closer than the original. There's no way that with a tiny quarter, like 25 centimeter crank arm, you're gonna move a 1 meter rod at 100 radians per second. Like it can't multiply that high. So if it's 2 and 3, that makes a lot more sense to me. 2 and 3. I would have expected one of them to be positive. Like I would have thought theta 2 is decreasing, but theta 3 is increasing. So I thought there should be a negative theta 2 dot and a positive theta 3 dot, because it's talking about the rotation. And because they're connected at these links, rotation of any, like once you have a rigid body, if you know the rotation of any part of the rigid body, it's the same rotation everywhere. Like it has to, in order to maintain itself, like one rotation rate is the same rotation rate. So as you're going through this, double check these numbers. But this is a great way to, and you can see, like I tried 4 or 5 different variations of this, all very quickly, because I'm plugging it in as a linear algebra problem rather than trying to solve for theta 2 dot in terms of theta 3 dot, making an error and like, oh no, this sign is wrong, kind of going that way. But I find that it's easier to go through the solution process once I get to this point of like, all right, here is my equation. And one of these, yeah, this should be a negative. That's a negative. So I bring this one over. Theta 3 dot is a negative. This one becomes a positive. But that's not a 0.2. This should be a 0.694. Maybe that was my problem. And that should be a positive 0.694. Ah, maybe that's it. I didn't rearrange arrange it correctly. Did I? And that looks better to me, but I really thought that this one would have been negative and that one positive. But anyway, you can double check my work. You certainly should. And then when we go into, when you take a look at this second problem with, let's go back to our main homework page. Yeah, so we're about here. So I can see that as I keep moving, this one, theta 3 dot, should continue to open. Meanwhile, theta 2 dot is probably closing or not changing much. Like theta 2 dot might be a very small value because this angle doesn't change very much to begin with. Meanwhile, theta 3 dot is probably not rotating as fast as theta 1 dot, but it's got to be like, it's moving a lot more, it's rotating a lot more than link number 2. As you come into this problem, the equations are exactly the same. We already set up, we did the hard part of creating what are these constraint equations, and the last part is plugging in these values. Like, okay, well, let me figure out what that sine theta is, what this cosine theta is, but we can use these same two equations, and we already went through that work. So we can start kind of right here and say theta 1 dot is 10, L1 is 0.25, and then start plugging in the rest of the values. And I'll let you do that to give yourself a shot, and also so you can correct all my mismatched math. Maybe keep track of the signs a little better than I did. And yeah, that's it. Good luck at the career fair today, or if you're watching this after the fact, then I hope it went well. And I hope you go and you talk about some of your experiences with dynamics and how you think about how that plays into your engineering careers. And have a great day. I'll see you in class on Wednesday.